All right, good morning, ladies and gentlemen. Welcome back. Sorry if any of you actually went to a lecture today. I've sort of sent out an email a couple days ago, but I wanted to make an announcement here in that there will be no in-person lectures today. So if you're in the sorry about that. You'll notice that I am most definitely not. I'm actually about 700 miles away in Western Pennsylvania. So yeah, I'm not going to be in class this week. I'm away for some personal reasons, I guess. So I'll be broadcasting the lecture at the normal time this week. We'll have labs, obviously, at the normal time this week because you have your exam. I just won't be in person in the classroom to deliver the in-person component. But I'll be back next week in person. So if you want to come back in person next week, it would be great to see all of your shining faces. All right. So with that out of the way, a couple of announcements for the class. Number one is that your homework number 4 is due right now. That's on failure criteria. A lot of people seem to have questions about that and struggled with that a little bit, and I promise you that's going to be on the test. So if you're having issues with that, make sure you take a look at the solution for the homework. I'm going to post that right after lecture today. So if it's still fresh in your mind, kind of that particular homework, make sure you take a look at that and really understand what's sort of happening there. Okay. Another announcement is that I'm going to do an exam review session tonight at 7 o'clock p.m. Central Time, even though I'm on Eastern Time. 7 o'clock p.m. Central Time. Come and we'll do this virtually, and I'll go over some of the exam practice problems that I posted on Blackboard. So take a look at those, give those a go today sometime if you haven't had a chance. And I'm going to tackle, maybe, I don't know, 3 or 4 of those in the evening today, maybe one from each of the sections that you see there for the material that you're going to have for your exam. Then obviously this week you're going to have your exam and your lab period. So the instructions for taking the exam, they're uploaded to Blackboard. Hopefully you've had a chance to take a look. Basic idea is turn your camera on, leave your mic muted. I'll distribute the exam to all of you. You'll work on the exam in your own personal space, kind of writing, working in front of you. And then after the exam time is up, take a picture of it and submit it to me by email just like you would for homework. So it should be pretty straightforward. I didn't have a whole lot of issues with doing this last quarter in the spring, so I think this will work out well. Any questions quickly? Looks like maybe we do have a comment. Matt says, can you record the review session? I won't be able to make it. Yes, I will record the review session tonight, and I will post it when it is done. I guess it'll probably go somewhere between an hour and an hour and a half, if I had to guess. Other questions? Okay. If there's no questions, I'm going to sort of pick up where the lecture left off. And just to remind you, I was not there on Friday, and I had a pre-recorded lecture on sort of the next step of the buckling notes. I'm going to go through that really quickly here and review some of the things from that particular lecture over the next maybe 5 minutes or so. But if you haven't had a chance to take a look at that lecture fully, I would really suggest that you do that. Okay? So last time, we talked about intermediate columns. And the idea here is that you could sort of think of columns in a variety of different categories, but if you thought about columns as like short, then you might have something that looks like this. And if you're loading it axially with some load, some stress sigma, then the allowable stress that you might consider is just the yield stress sigma 0. All right, if a bar is particularly short. And this would be for more or less like small slenderness ratios. On the other extreme, you might think of like a long bar, like a long column. All right, and that might look something like this, where we load here with some stress. And our allowable load here at failure is that of like the buckling. So we call that like sigma critical. And this is like our buckling stress to failure. And we saw that this was pi squared E over the slenderness ratio, which is L on R squared. All right. Then the question that I sort of posed in the lecture last time is what happens if you have something in the middle? Like, what do we consider long? What do we consider short? And how do we sort of like delineate a long column versus a short column? And so here we have what we call the intermediate range. The idea here is that, yeah, maybe it's somewhere in the middle, somewhere in between. All right. And we're going to load this with some stress here, just like the other two situations. And the question is, like, what is the allowable stress? Is it the yield stress? Is it the buckling stress? Is it something else? And that's what we sort of tackled last time. And so this is sort of like this intermediate slenderness ratio kind of idea. So here this is large slenderness. Right? If it's very, very slender, it's going to just buckle like we've talked about before. And this is sort of like middle slenderness. Kind of how I feel after eating too many pizzas these days. Middle slenderness. Okay. So the idea is you might want to plot slenderness ratio and look at what the stress at failure is given various slenderness ratios. Okay. And so if the slenderness ratio is very small, then you're going to fail by yielding. If the slenderness ratio is very large, you're going to fail by this buckling that we've talked about before. And if it's in the middle, what happens? All right, well, let's talk about that. So if we plot your sort of allowable stress, we might call it like sigma allowable versus slenderness ratio, just like L on R. Then you might see something that looks like this, where you have the slenderness ratio L over R on the x-axis, and you have the allowable stress on the y-axis. Now we know at very small slenderness ratios, we just have these like short blocks that are just going to fail by your typical yielding, which you've sort of think of traditionally as like the yield stress of the material. Okay, so here we have like the yield stress sigma 0. And so this might be like the failure line that dictates failure for small slenderness ratios. You might also have a situation where your slenderness ratio is very large and you're going to fail by this like Eulerian buckling theory that has some sort of kind of curve that looks a little bit like this, where we know that the equation that dictates this is pi squared E over the slenderness ratio L on R squared. Okay, so we see that this particular line here has like a 1 over x squared sort of look to it. All right. So in an ideal world, your dictation of how these particular materials would fail can be governed by the slenderness ratio by looking at what would be like the minimum stress to failure in each one of these situations. And this would be like the ideal case. Let's call it the ideal fail line. All right. But in reality, you know, people have done experiments where they've looked at testing columns of various lengths, and you see that in reality, data actually looks something more like this. Okay, and so if we wanted to maybe put a trend line to this, it would look something maybe a little bit more like that. Okay, so this is reality. It's the next reality TV show. Intermediate buckling. Okay. So we see on the far left, kind of over here, where the slenderness ratios are small, we do sort of adhere to that kind of very short slenderness or this compression block range. And so we would call this the compression range. This area down here is the compression range. And then kind of way out here on the right-hand side, sort of where reality again lines up with our Eulerian buckling theory, we say that this is the Eulerian range or the slender range. But all these slenderness ratios that exist in this sort of range here, where the data in reality doesn't actually line up with what you might predict, we would call this the intermediate range. And that's sort of the interesting range for us. All right. So this is all still kind of review from last lecture. So this intermediate range here, it varies by material. And so some examples I sort of pulled up from from the lecture last time. So if you watched the video, you saw me pull in some examples of some of these actual sort of failure curves for a variety of different materials. So I'll just go through maybe one or two right now just so you see. Here is an example of one for like aluminum. Right? So here's an example. This is aluminum 2014. Boy, I wish I could go back to 2014. No, I don't, because I'd still be in grad school and, not enjoying my life as much. All right, so here's an example for aluminum 2014 T6, and it might. Whoa, why did you go there? Go here. What? All right, let's just put them over here. There. Okay. So there's an example for aluminum 2014 temper 6. So the idea here is that down at this end, where your slenderness ratio is 12 or less, you're going to have this yielding, this short Brock kind of compression type failure. If your slenderness ratio is greater than 55, you're going to have this slender buckling, which is like, again, pi squared E on L over R squared, your typical Eulerian buckling equation. And then you have this intermediate range here that doesn't really follow either one of those particular lines. And so there's this sort of trend line here that exists that people have come up with utilizing real data that we sort of now use as sort of gospel for this particular material. And again, this is specific for aluminum 2014 T6. They vary by material. And so the question is like, what is the equation that governs this particular portion of the curve? What is the equation that sort of governs that line? Well, depending on the material that you're looking at, the equation that's going to govern that line is going to be different. And so you more or less have to populate a chart that tells you all of the equations for all of the materials. Your Briley book has an example of a couple of probably the most relevant materials. And so I'll go through that here now and just show that. And this comes from your book. This is table 9-1 from your book. So if you take a look at this chart shows 4 materials of interest, even though there are many, many more codes like this that exist. So the idea here is that let's take a look at sort of this first one here, code number 1. This is for a structural steel with yield point sigma Y. All right, so it's structural steel, whatever structural steel you want to consider. In this situation, we have what is your typical like Eulerian looking equation if you're very slender. So the slender range is kind of on the right-hand side. And this tells us that if you're slender, that your equation for failure is governed by this particular expression. All right, pi squared E over 1.92 slenderness ratio squared. All right, kind of a strange expression, but that's what it is. We're dictating where the slenderness range is by this particular domain distinction. Here we're saying in this chart that if L over R is greater than this like C value, that you're in the slender range. So what is that C value? Okay, well that C value is here depending on the yield strength of your material. I'll blow this up a little bit, but this here is 2 pi squared E on sigma yield. So this sort of, it's like a distinction telling you what is the actual slenderness ratio from moving from the intermediate to the slender range. All right, it's sort of this like governing value. So this is sort of an indication of what you might need to use to determine whether you're slender or intermediate. All right. Now, if you're less than that CC value, right? So if you're between 0 in that critical value that was given by this capital C, then you're going to use this equation here. And that's this sort of crazy equation that dictates like the intermediate range for this particular material. So here it's sigma y on Fs multiplied by 1 minus 1/2 slenderness ratio divided by C squared. It's this kind of crazy equation where Fs is given by this particular expression. Okay, so a lot of just randomness to these equations, but if you just follow this chart, it can get you where you need to go. So that's about where we left off last lecture. I just wanted to do a quick recap in case someone hadn't watched it, and we'll do now an example problem where we're actually going to use one of these. We're going to use this chart to actually figure out a problem. So here's an example from your lecture notes. I'll pull this up quickly for you to copy down, and we're going to look at a Douglas fir timber column. So Douglas fir is a common material used in housing construction, and we'll look at this particular situation where we're loading up a long, slender timber column. Tinder column. Gosh, let's swipe right on our Tinder column. Okay, no, timber column, and we'll take a look at how this guy fails. Okay, I'm going to copy this statement over to the writing pad. So keep copying, I guess, if you need to. But here's the problem we're going to work on. Okay, so we're given the modulus of the material, and we're given this FC value, which is sort of the maximum kind of compression load that is required to sort of work in this table 9-1 that we have before. Right? So it has an effective length of 3.5 meters. Effective length meaning it's already been accounting for the boundary conditions, meaning we don't really have to worry about boundary conditions in this situation. We're already told the effective length is 3.5 meters, and we're told some information about the cross section. Okay, so let's go ahead and maybe draw this cross section quickly so we sort of get an idea of what we're working with here. So this cross section maybe looks something like this. And this guy is 150 by 200 millimeters. So maybe we'll call this 150 millimeters, and this is 200 millimeters. We want to determine the maximum compressive load permitted by this particular code. All right, so we want to take a look at this code first, and we're specifically looking at Douglas fir. So let's go back up to this chart here, and we'll take a look at the Douglas fir portion. And maybe I'll actually bring in my PowerPoint slides so we can sort of zoom in on that particular area. So let's actually bring in the notes here. By the way, this table, if you didn't notice, was in your notes. And so let's take a look at this guy here. And specifically, we'll look at the Douglas fir portion, which is down here at the bottom. So we have a timber with a rectangular cross section B by D, where D is less than B. It's going to be sort of important in just a second. We have some information here about how we distinguish the various regions. If L on D is less than 11, then the allowable stress is just this FC value. If we're between 11 and K, then our allowable stress is dictated by this equation, where K is calculated with this particular value. And if we're between K and the value of 50, then our allowable stress is given by this particular equation. So let's go back over to our problem statement here. And we're told in that particular chart that timber with a rectangular cross-section B by D, where D is greater than B. Okay, so timber with D greater than B. Okay, rectangular cross-section D greater than B. Okay, sorry, B greater than D. So here, this 200 millimeters would be like our B variable, and this 150 millimeters would be like our D variable. Hopefully we sort of understand that, because D has to be less than B in a rectangular cross-section. Okay. All right, so with that particular chart, we saw if our effective length, I'll call it LE on not R, but on D here. Remember, we're working with D for this particular chart. I'll remind you that here, timber with rectangular cross-section, we're interested in just D, which is one side length of the cross-section, okay? B by D. So if this is less than or equal to 11, we fail by sort of this compressive stress. The allowable is just this FC value. If LE on 11 less than or equal to LE on D is less than or equal to K, then our allowable yield stress here is given by something else, which is this kind of crazy equation. I won't write it down here, but we'll revisit later. And if K is less than or equal to L on D is less than or equal to 50, which is also part of the chart, then your allowable stress is some other equation that's given in that chart. So to work this problem, we're going to need to calculate, obviously, this L on D value. And we also need to calculate this K value so that we sort of know how to delineate between the intermediate and the slender regions. So let's get on with that. So here, L on D, we're told the effective length of this column is 3.5 meters. So here's 3.5 meters divided by the variable D, which is the shorter portion of the cross section. Here's 0.15 meters. I'm going to work in meters instead of millimeters. This will give me an effective length, or sort of a length that I need for this particular problem, which is going to be 23.3. Okay, so if the value here is 23.3, then it either falls in this category or this category. And which category it falls in depends on my calculation of that variable K. The 23.3 is kind of my quote-unquote slenderness ratio for this particular problem. All right. So now we need K. K, if we go back to this particular chart, it tells us how to calculate this value of K. It's sort of this 0.671 square root of E on the failure strength. All right. So let's use that. This is square root of the modulus here, which is 11 GPa given to us in the problem, divided by sort of the failure strength of this material, which is also given to us in the problem, 7.6 MPa. All right, so don't forget your units here are a little bit mismatched, so you got to make sure that you're in the appropriate range of 10 here. Yeah, but if you work this, you're going to have a unitless value for K is 25.5. All right. So if K is 25.5, in this particular example, we have this sort of pseudo slenderness ratio of 23.3, then you can see that we're going to fall into what would be this range here, which actually is this intermediate range. All right. So with that, now we have to revisit our table and look at what the actual equation is that governs failure in that range. So here back to table 9-1. And you'll have here, if you sort of look into this table, you'll see that this guy here tells us that if we're between 11 and the value K, which we are, that the allowable stress is this FC times the quantity 1 minus 1/3 the pseudo slenderness ratio divided by K to the 4th power. A strange looking equation, but you know, that's what people have established with experiment. It's sort of a semi-empirical method. So then we have this allowable stress for failure is this FC times 1 minus 1/3 of our pseudo slenderness ratio L on D divided by this capital FC, all to the 4th power. This is our allowable stress. We have all these numbers already, so we can just plug it in. our allowable stress for failure. This is 7.6 MPa multiplied by 1 minus 1/3 times the quantity L on D, we already calculated above, is 23.3, divided by the value K, which we calculated, is 25.5. All this to the 4th power. All right. So if we work this out, the allowable stress in this particular case is 5.83 MPa. So that's the total stress that this particular column can handle, given its slenderness ratio and other geometric properties like the dimensions of the cross-section and the length of the piece. The problem actually asks us for the maximum load that it can handle, so we need to sort of transfer this allowable stress into an allowable load. And to do that, we simply multiply the stress by the cross-sectional area to get our allowable load. So that here is going to be 5.83 MPa multiplied by the cross-sectional area, which is 0.15 meters times 0.20 meters, okay, 150 by 200 millimeters. And if you work this, you'll get that the allowable load in this particular problem is 175 kilonewtons. All right, so that's kind of how you use the chart to get through some of these problems. How are we doing? Any questions on this? I have not seen any questions in the L chat. Okay, let's continue then with the last sort of complicated topic for buckling. And I'll say that this next topic is probably the topic that confuses people the most in this entire class. And that is eccentric loading of columns that could potentially buckle. Complicated. All right. Everything we talked about so far has been for central loading. So let's remind you what that means. Okay. And the topic here is eccentrically loaded columns. Eccentric, like my personality. Right? Right. So if we have some, let's just say rectangular cross-section. That looks like this. That may be long and slender and possibly going to buckle. Okay. Everything we've talked about so far has assumed that the load that we put on that column acts right in the center of that cross-section. So if we have the center of this cross-section here at, like, let's say 0.0, we have assumed so far that our loading situation is right down the center of that cross-section, which here is like some value P, and we'll say that this is like a centric load. Centric or central load. That's different from a load that is not acting directly in the center. And that load could be anywhere. It could be anywhere in that cross section, or it could be displaced off of that cross section if you have some way to sort of like load it with some additional moment arm. Okay. So an example of an eccentric load might just be like something like right here, all right, at this particular point. And let's say that here is some load P, which is eccentric. Right. And that's just hanging out there in space. All right. And the idea here is that, and let's not call it P, let's call it Q. The idea here is that if you relocate that load Q to the center of the cross-section, just like you might do for your combined loading problems, you're going to end up with that load that still exists there, but now you might have bending moments that are created by relocating that force to the centroid of the cross-section. Okay, so relocate Q to center of cross-section. Then if you do that, you're still going to have that load Q that hits here. Okay, but now you're going to have bending moments which are created by relocating Q. And so if we think about the bending moments that might be created by relocating Q, we might have a bending moment in this direction that is made by sort of the moment arm that moves here, this sort of distance there. But we also may have the moment arm that is sort of like this distance here, which might also create for us a moment in this general direction. Okay, so we could have moments that sort of act on this particular cross section as a result of relocating that Q to the center of the cross section. So we know about this from combined loading. Okay, and so because of this, you end up with additional stress on the cross section that you might not necessarily have considered if Q was a centric load. So if Q is a centric load, obviously this contributes stress in the form of like P on A. But those bending moments now also contribute stress on this cross section in the form of like My over I, right? So this will contribute stress in the form of like My over I. And same thing with this guy. He's going to contribute stress in the form of like My over I. Right? So you have to be mindful and know that if you relocate this force to the center of the cross section and generate these moments are going to induce additional stresses in the cross section with like that linear load distribution or linear stress distribution through the cross section. And you have to be able to accommodate that and account for that. Right? So here's the general point. If loads are eccentric, bending moments are present. Okay. You're going to have these bending moments present, and they're going to contribute additional amounts of compressive stress, right? So if you think about a bending moment, one side's going to sort of give you tension, one side of the cross section is going to be in high levels of compression. So if you, for instance, thought about like this bending moment here, it would induce high levels of compression along this side of the bar, and it would induce high levels of tension on this side of the bar, okay? Now this bending moment might induce high levels of compression on this side of the bar and high levels of tension on this side of the bar, okay? So if I was considering where the compression is greatest in this cross section, it's probably going to be greatest at that particular point where I have compressive stresses that are acting from these bending moments sort of maximized at that location. That would be where the sort of cross section is most likely to first fail because that's where the compressive stress is highest, that particular point, okay? So my point in all this is that you need to account for this eccentric loading and how it contributes to the compressive stress. And generally the idea here is that you want to attack this eccentric load in the same way that you attack sort of the combined loading problems. Okay, so let's go through like the methodology of attack. And this methodology that we're going to employ has a name. It's called the allowable stress method. Okay. When you have an eccentric load, the current state of stress on the bar is going to be some combination of like the axial load plus the bending load. So with eccentric loads, we're going to relocate load to center cross section, and this will give bending moments. So here's relocate. Sorry about the handwriting. Then you want to find what is the maximum compressive stress in the cross section. And for that, you're going to sort of like use your combined loading analysis. And that stress state that currently exists in the cross section from these eccentric loads, we would basically label this as like sigma current. So that might look something like the current stress state is equal to sort of the axial load that you provide, P on A, plus some bending moment that you generate from relocating that force to the center of the cross section, right? Once you've calculated sort of the maximum compressive stress on the cross section using this sort of analysis here, you want to compare that stress to the stress on the cross section that would cause failure, right? And this is where the confusion usually occurs. I'll say compare that max compressive stress to the maximum allowable stress in the cross section as given by that table 9-1. That maximum stress is this like allowable stress, okay? All right. What I'm about to say here now is probably the most important thing that I'm going to say all lecture. You have to calculate the allowable stress and the current state of stress separately, okay? Very important. 3 stars. Must calculate the current state of stress and the allowable state of stress separately. Okay. The current state of stress comes only from the load that's on the structure and the geometry of the structure. I'll say from load on structure. So that in an example is like the sigma current is P on A plus My over I, right? That is the current state of stress on the cross-section. It has nothing to do with the amount of load that would cause buckling failure. It has nothing to do with the yield stress. It has nothing to do with failure criteria in any way. It is just what is the load and the stress on the structure? What is the maximum compressive stress on the structure right now? Right? Has nothing to do with table 9-1, nothing to do with yield stress, etc. This has nothing to do with anything in that table. Contrast that with the allowable load. This is from Geometry and Material Properties. And this is more or less from table 9-1. The allowable stress has nothing to do with the current loads that are on the structure, okay? The allowable stress is just the amount of stress on the cross-section that would cause it to fail by buckling or yielding or intermediate failure, all that sort of stuff that we've talked about. It has nothing to do with the load that's on the structure. Okay? Once you've calculated these two things, the allowable stress and the current state of stress, then if the current state of stress is greater than the allowable stress, you fail. Okay? Oh my goodness. Calculate these things separately. Oh my gosh. Okay? I say this 1,000 times. I always say it 1,000 times every quarter that I teach this class, and I cannot emphasize this enough. You have to calculate the allowable stress and the current state of stress separately. All right? Please. If you take nothing away from this lecture, take away that you have to calculate the allowable and the current state of stresses separately. Maybe you don't know how to do that, but at least you know to do that separately. All right, so let's look at an example problem where we're sort of going through this whole rigmarole with an eccentric load. All right. I want to see if I can just copy this directly down. This is in the notes, so you can just take a look at this if you want. It's right in the notes. Okay. I'll give you a second to copy this down. It's kind of a long problem statement. And we'll do this problem when we come back on Wednesday. But hopefully we kind of see this eccentric load here, this little value of little e here, giving us this load which is kind of off center. it's a little bit unclear from the picture too, is that this dimension here is the dimension little c. Which is given here. Okay, we'll leave it here for now. I'll leave this up for a little while if you guys want to continue copying this problem down. And we're just going to jump in on Wednesday right into tackling this problem. So again, reminder, review session tonight, 7 o'clock p.m., your time. I'll be here on Teams. I'll record that and post a video. I'm also going to post the homework solutions here for homework number 4 in just a second. Make sure to take a look at those. Otherwise, so long. For those of you taking the exam tomorrow, I'll see you then.